Hi, my name is Daniel. Welcome to this journey through smart electrical systems and automation. Today we are going to study the chapter which is Industrial Automation Concepts. In this chapter, we'll explore the fundamental concepts of industrial automation, specifically focusing on SCADA systems, PLC programming, ladder logic, timers, counters, safety interlocks, and HMIs. Let's begin. What is SCADA? SCADA stands for Supervisory Control and Data Acquisition. It's essentially the brain and eyes of an industrial plant, allowing engineers to control processes locally or remotely. With SCADA, you can monitor real-time data from sensors, valves, pumps, and motors, interact with them via an HMI, and store event logs for analysis. This combination of control, monitoring, and data logging makes SCADA vital for efficient, safe, and continuous industrial operations. SCADA system architecture and components. The architecture includes a central host computer, a communication network, remote terminal units, RTUs, and HMI workstations. The central host collects and displays data, communication protocols like Modbus or DMP3 link all devices. RTUs interface with field devices, and HMIs allow operators to visually monitor and control processes. Hardware components include PLCs, I/O devices, and communication links, while software includes HMIs, historian databases, alarms, and reporting tools. PLCs versus microcontrollers. PLCs are rugged devices built for industrial environments, supporting modular I/O and deterministic real-time operation, often programmed in ladder logic. They excel in safety-critical 24/7 operations. Microcontrollers, on the other hand, are more common in consumer electronics, less robust, and lower cost, programmed in languages like C or assembly. Choosing between them depends on application needs. Industrial safety and uptime usually mean PLCs, while cost-sensitive simple tasks might use microcontrollers. Introduction to ladder logic and basic elements. Ladder logic is a visual programming language inspired by relay circuit diagrams. It uses vertical power rails and horizontal rungs, scanning top to bottom. Inputs like switches are represented by contacts, outputs like motors by coils, and advanced operations by function blocks. Examples include AND logic, two inputs in series, and OR logic, parallel inputs. This intuitive format makes it easier for electrical engineers to implement control logic. Emergency stop logic. E-stop circuits are essential safety measures. They must be hardwired, redundant, and use normally closed contacts to ensure fail-safe operation. Once activated, an e-stop disconnects power to dangerous equipment immediately and requires a manual reset. Ladder logic for e-stops includes a latching circuit, reset button logic, alarms, and status indication on the HMI. Indicator. Lights in industrial control. Indicator lights visually communicate machine status. Types include pilot lights, stack lights, beacon lights, and HMI status indicators. Color codes are standardized: red for emergency, amber for warnings, green for normal, blue for required actions, and white for general status. In ladder logic, these lights are assigned output addresses, and their activation conditions are programmed to reflect machine states. Timers in PLC programming. Timers control delays in automation. An on-delay timer, TON, waits before activating an output. An off-delay timer, TOF, keeps an output active after input ends. And a pulse timer, TP, outputs a fixed duration pulse. Applications include delayed starts, fan run-ons, and pulse generation for process control. Counters in PLC programming. Counters track occurrences of events, like the number of items passing a sensor. CTU counts up, CTD counts down, and CTUD can do both. Each has a preset value, current value, reset input, and done bit. They are used in production counting, batch processing, preventive maintenance, and sequential operations. Timer and counter applications. In conveyor systems, counters monitor products and adjust speed. In mixing processes, timers control ingredient addition. In robotics, counters track cycles while timers ensure dwell times. These examples show how timing and counting enhance automation precision. Safety interlocks. Safety interlocks ensure machines only operate under safe conditions. They can be mechanical, electrical, logical, or procedural. Implementation involves risk assessment, selecting safety-rated components, programming fail-safe logic, and validating operation. Redundancy and diagnostics are key for reliability. Human-machine interface, HMI. HMIs allow operators to monitor, control, and manage industrial processes visually. A good HMI design uses consistent layouts, clear data presentation, and color coding. Technologies range from panel touchscreens to mobile and web-based HMIs, even augmented reality. HMIs make automation systems more intuitive and efficient.